Right. So what we are going to cover today is anaerobic treatment. So probably the last important topic in this class. Earlier we focused on aerobic treatment, right? Aerobic. What is aerobic treatment? What is aerobic treatment? You have oxygen, right? You have molecular oxygen as the electron what? Acceptor, right? Acceptor. And natural nature, you learned anoxic tank. Yes or no? Right? Anoxic. What is anoxic? What is anoxic? Huh? The reaction needs the oxygen. Who agree with him? Anoxic. So what are the electron acceptors there? So what do we do under anoxic condition? What do we do? Reduction, right? Reduction, reaction. We have nitrate, right? And it ends up with nitrogen, right? Nitrogen. So nitrate is the electron acceptor. Positive 5 to 0, the oxidation state for nitrogen. Right? From positive 5 to 0, that's reduction. Nitrate is the electron acceptor. Right? So today we're going to learn anaerobic. So anaerobic. What does this mean? No oxygen. Okay. So a niche difference, aerobic, anaerobic, we talk about microorganisms. Aerobic respiration, anaerobic respiration of microorganisms. Right? But for anoxic, we usually talk about the environment, anoxic environment, anoxic tank. Okay. So what is anaerobic? We're going to learn today. And so what are the applications of anaerobic treatment? Right. So basically, it's different from aerobic treatment. Aerobic treatment, you see, its application everywhere in municipal wastewater treatment. Right. What are the two main treatment schemes? Aerobic treatment. You know, treatment scheme, not the parameter. Active sludge belongs to suspended, right? Suspended gross treatment scheme. Trickling filter belongs to attached gross treatment scheme, or biofilm treatment scheme. So these are the two main categories. Each category will have different technologies such as active sludge. Right? Today we talk about anaerobic treatment. I cut the slides, so we have only 40 some slides. It used to be very long. I guess we have already a lot of content, right? Have you started to prepare for the exam? Okay. So in our coming lecture, we'll talk about very briefly about the exam. What's the composition? What do you expect to see regarding the problems in the exam? But for anaerobic treatment, I've shortened the content. All right. So first, we started with the combustible air of natural phenomenon, right? Natural phenomenon. It occurs in the region of decaying plant material in underwater sediments. Right? It was observed very early and described in 1776. Right? Perhaps there are some records as well. So what is this gas? What is this gas? Methane, right? So this is methane. CH4. It's methane. Okay, it's methane. Right. And what happens there? It's anaerobic process. Okay, anaerobic process which produces methane, and methane is combustible. Okay, combustible, and it happens in natural environment. But very similar to aerobic treatment of wastewater. Right, we can harness the power of anaerobic microorganisms, right, and to basically have the anaerobic digestion or anaerobic treatment process for wastewater treatment. Right, for wastewater treatment. Let's directly come to the concept anaerobic digestion, solubilization and fermentation of complex organic substances by microorganisms in the absence of oxygen. So there are two steps, right? Two steps. The first step is solubilization. What is that? Something is soluble. Something is soluble. Hydrolysis. Right? So the organic matters react with water, right? With water, and it becomes soluble. And then fermentation. You heard of this fermentation? You drink wine. How wine is produced? Fermentation, right? So fermentation, two-step. Complex organic substances become smaller, soluble, and then fermentation. One of the oldest treatment processes for waste treatment and disposal. Product, methane, is useful, a renewable energy, right? And CO2, and some trace gases. What are the trace gases? We will learn. Okay, perhaps hydrogen sulfide, and cells. Right, cells very similar to aerobic treatment. We have cells grown because of consumption of the wastewater organics. Right. So here the anaerobic microorganisms convert wastewater organics into cells as well. But they have different metabolisms. Right. Then we'll say very different values. Do you still remember what is Y? What is yield? What is yield? Yield equals biomass produced, cells produced, right? Over what? Cells produced over substrate consumed, right? Substrate consumed. So that's yield. And here we'll say what's a yield for anaerobic treatment. Okay, anaerobic treatment. During digestion process, effective inactivation of pathogens. Okay, inactivation of pathogens. Many environmental factors affect biosolids digestion. We'll learn the environmental factors. So before our discussion, what kind of environmental factors you can think of? About temperature. Do you think temperature will affect anaerobic treatment? Yes, right? Temperature. What else? pH. pH of the wastewater. What else? How about oxygen? Yes, right? We are going to learn about other factors as well. Anaerobic treatment definition carried out in the absence of oxygen. So no oxygen. Right? If you have oxygen, oxygen will compete. Right? In the process. Stabilization of organic materials by converging to methane, CO2, and ammonia. Okay, ammonia. If we write them into equation, it will look like this: organic materials plus some nutrients. So you also need nutrients: iron, manganese, cobalt, etc. Right? And very importantly, we need anaerobic microorganisms. Microorganisms. You say a distinction for wastewater treatment from water treatment is the involvement of microorganisms. Aerobic treatment we have, right? Aerobic microorganisms. For nitrification, denitrification, we involve different microorganisms. Phosphate removal, what do we utilize? BEPR process. What is the type of microorganism? Phosphate removal. No one knows? What is PAO? What's PAO from last lecture? Phosphorus accumulating organisms. So for phosphate removal, we utilize PAOs. Here we utilize anaerobic microorganisms. Okay, anaerobic microorganism. And we're going to see actually it's an ecosystem. Okay, not only one type of microorganism, anaerobic, but many. The end product, methane. Methane is useful. Right? It can be used to generate electricity on site. And we have CO2, we have ammonia, we have some new biomass. Okay. So for aerobic treatment, how does the equation look like? We have organic matters, we have nutrients, aerobic microorganisms. We do not have CH4, right? We don't have this. How about this? Ammonia. You have ammonia. If you have nitrifiers, what do you have? If you have nitrifying microorganisms, what do you get? What is nitrification? What is nitrification? What is nitrification? You get nitrate. That's nitrification. And here you have the nitrifying microorganism. Right? You did this when you calculate NOD. What is NOD, by the way? What is NOD? Nitrogenous oxygen demand, right? What is COD? If you do not know COD, you have a big trouble. Chemical oxygen demand, right? What's the combination? COD. Anyway, total oxygen demand, right? Total oxygen demand. Okay. We could classify aerobic process into two: fermentation and respiration. Fermentation and respiration. First, let's introduce fermentation. Everybody drinks wine, beer. That's a process. You get ethanol. Okay. No external electron acceptor. Right, we talk about electron acceptor. That's very important in all these reactions we utilize. So far, what are the electron acceptors? What are the electron acceptors? That's one, right? Aerobic treatment. So we need aeration because we need to supply oxygen. Right? Nitrate could be electron acceptor. During the denitrification process, we convert nitrate into nitrogen gas. Okay. So these are external electron acceptors. Fermentation, there's no electron acceptor, external. So what are the electron acceptors? The products generated during the process. The intermediates. You have wastewater organic, like say A, chemical A. You have an intermediate, which is B, right? So B serves as the electron acceptor, not oxygen, not nitrogen. Organic matter acts as both electron donor and acceptor. Okay. This is one example of glucose. Glucose. The glucose electron donor, so it gives out electron. And we have some intermediates, for example, pyruvate. Okay. Pyruvate. That's the product of oxidation of glucose. But pyruvate could act as the electron acceptor. So this is oxidation of glucose. It releases electrons, right? Where do the electrons go to? It go to pyruvate. Okay, pyruvate. And what do you get? Ethanol. Okay, ethanol. And the oxidation step, this step releases energy. So the major portion of energy still contained in the fermentative product such as ethanol. Right? So the whole process, some energy is released, but still a lot of energy is contained in the end product such as methanol. Right? Process of making something you drink, right? Ethanol. So this is fermentation. Fermentation. The intermediates serve as the electron acceptor. Okay. So very different than anaerobic respiration, external electron acceptor needed. It's not the intermediate product. Electron acceptors could be sulfite, nitrate, or CO2. CO2. The energy release under such a condition is higher than anaerobic fermentation. In terms of capability of accepting electrons, oxygen is the strongest. So it has the highest capacity. What does that mean? What does that mean? If there is oxygen, the electrons will go to oxygen. Okay, will go to oxygen. Nitrate, sulfite, and CO2. Okay, CO2. This is the same example of glucose, but the process is anaerobic respiration. So we started with glucose, and we have a intermediate still, pyruvate. Okay, so glucose you have 6 carbon. Pyruvate, if I do not remember wrong, it should be 3. You have 3 carbon. Right, so it's a smaller molecule. And look at the electron. Okay, look at the electron. So it does not go to pyruvate. It goes to electron acceptors such as sulfite, CO2, and nitrate. And further oxidation of pyruvate, you get CO2 and water, and also this step, it gives out electrons. All these electrons go to the external electron acceptors. Okay. And what's the end product? If you have sulfite, you get hydrogen sulfide. Hydrogen sulfide. If you have CO2, you get methane. Right? If you have nitrate, denitrification process. So that's nitrogen gas. Okay, nitrogen gas. So in Hong Kong, we use seawater for toilet flushing. I believe everyone knows now, right? From this class. And seawater contains not only high concentration of sodium chloride, but also sulfite. Right? Sulfite. So we have big tunnels to transfer our sewage, right, to the sewage treatment works. Very large tunnels. And within this tunnel, we have hydrogen sulfide being produced. Right? That's a big problem actually. DSD wants to control. And if you are from Hong Kong, you probably read some news in the previous years. Right? There were accidents. Some workers died because of this high concentration of hydrogen sulfide produced. And these tunnels are underground, deep underground. There could be oxygen could be missing from there. So what happens is this: okay? Reduction of sulfide into hydrogen sulfide. The question? Question? No? Pretty clear. So you should be able to compare these two schemes, fermentation and respiration. Okay. What the differences? What the differences? Anaerobic digestion. So typically we have this 3-step. It is shown in different colors. As I said earlier, right? It's solubilization and fermentation of wastewater organics. First step, solubilization, is hydrolysis. What does hydrolysis mean? Reacts with water. Hydro, that's water, right? Reacts with water. If we start with some complex organics like high carbohydrates, protein, and lipids, these are micromolecules, starch, right? Large molecules. And you need to make them smaller so that this microorganism can utilize. The first step is hydrolysis. So they react with water, and we get some simple organics, right? Simple organics. So these may contain a few to perhaps dozens of carbon atoms in one molecule. Simple organics, you could only have a few. Simple organics. And next step is acidogenesis. Acidogenesis. So generating acids. So we have some short-chain acids produced. Volatile organic acids like propionate, butyrate. These are short-chain acids. So the molecules get smaller, even smaller in this step, right? And the reaction will continue to occur, and you get acetate. Acetate, you have only 2 carbon, right? 2 carbon. And hydrogen gas and CO2. And eventually, through methanogenesis, generating methane. You get methane and CO2. Methane and CO2. 3 major steps. This is the same figure. Okay, same figure, but we have some percentages for each pathway. Okay, for each pathway. 3 steps: hydrolysis and fermentation, acidogenesis, and methanogenesis. So every step will involve some microorganisms. Okay, involve some microorganisms. Oh, in a more complex diagram. Okay, in a more complex diagram. So here we distinguish proteins and carbohydrates from lipids. Proteins and carbohydrates, you get amino acids and simple sugars. Right? Protein, we have nitrogen. Right? Nitrogen. So you have amino acid. Carbohydrates, you probably get sugars. Lipids, you get long-chain fatty acids. This step, hydrolysis and acidogenesis. Through fermentation, you get volatile fatty acids like propionate, butyrate, acetic acid, and hydrogen. And here, hydrogen could be converted into acetic acid through homoacetogenesis. That's step 3. Okay, step 3. And last step, we get methane. So what are the microorganisms involved in each step? The first step, hydrolysis and fermentation. Right here, the whole process is carried out by a series of bacteria, so a group of bacteria. As indicated in the figure with numbers, this is group 1, group 2, group 3, group 4, and group 5. Okay. There exists a coordinated interaction among these bacteria, so they work together. If one step fails, that will disrupt the whole process. Okay, whole process. The process may fail if a certain group of this bacteria is inhibited. For the first type, step 1, right, we convert complex biodegradable particulates into proteins, carbohydrates, or lipids. This group of bacteria is responsible for the first stage, hydrolysis and acidogenesis. These bacteria are either facultative or strict anaerobics. What does facultative mean? This word. What does facultative mean? I think I briefly explained to you. They can utilize oxygen and non-oxygen electron acceptors. Okay, so they can use oxygen, but strict anaerobics they cannot. Okay, they cannot. The family of all this, which I cannot pronounce. All this Latin words. Okay? But we understand the first step is fermentative bacteria. Okay, fermentative bacteria. Second step, right, from volatile acids to acetic acids or hydrogen. This group of bacteria metabolize propionate and other organics. So these organics have more than 2 carbon atoms in their molecule. Okay? And certain aromatic compounds like benzonate. You know aromatic, right? What's aromatic? What does aromatic mean? What is this? What is this? It's aromatic ring, right? Aromatic ring. Aromatic compounds contain aromatic rings. Right. So this is I believe this is propionate. We have 3 carbon. Right. We get acetate, 2 carbon, and CO2 and hydrogen gas. This is called acidogenesis because we have acid forming, right? Centrophic association of acidogenic organisms with methanogenic hydrogen-consuming bacteria helps to lower the concentration of hydrogen below inhibitor levels, so that propionate degrading bacteria are not suppressed by excessive hydrogen level. Right. So this step, you say this step with producing hydrogen gas, right? Hydrogen gas. It needs to be consumed. What's the result if we do not consume hydrogen gas? Will the reaction continue? You learn some thermodynamics. If we have very high concentration of hydrogen gas, the reaction will not proceed from the left to the right, right? Right? So that could be a problem. But here, hydrogen gas will be consumed by the methogenic bacteria. Here shows all these bacteria work together. Okay? They work together. The third step, converting hydrogen into acetic acid. CO2 plus hydrogen, we get acetic acid and water. Right? This is the bacteria are hydrogen and CO2 users. So this bacteria consume CO2 and hydrogen gas, right? Clostridium aceticum, etc. Right? They have a high thermodynamic efficiency, so there is no accumulation of hydrogen and CO2 during growth of multi-carbon compounds. Okay. So hydrogen can be consumed by this step or by this step. Okay. Any question before take a break? No? Okay. So let's take a break. If you were absent from last lecture and did not pick up your homework, it is here on the desk. Okay, let's take a break. Send me email. I will put the because over 100 TS, right? I will not upload, but I will go through the solutions. The lecture will be around. Are you here? You can check.
那我印象好像10点左右。搞不大写的东西，我认识。
你可以写个 email 贴上面，看这 case 有什么。对，但是一般来说呢，都是用的美式的，真的是是比较快一点。我不会告诉你怎么做，因为 unfair to others。这个也很简单，就是用那个保险公司给他比如说你 check parameter， 就说那你上来对，其实可以判断这个不缺，这个有没有算一下细节。这个应该是对的，这个是这个应该是对的，因为它就是要，它是一个 insoluble， 所以这个是对的，他们写例子的态度。例子这不对，对，different units, right? You have pound per day. 那你今天就是这 is very small difference 今天我老就会交多导致了那个答案有些不一样，应该是我这边解决的。OK. So what you can do is to send me email. I will ask RPA to check how much. I go through the process. If you are right, again put your scope back. 所以 not a problem. 这个上次说的就是打面试就是这样子的。If you have any question, you can send me. No more. It should be okay. What I could think of is there are too many homeworks over 100. IPA has finished this within 10 days. So it must be a very quick process. You didn't have that much time to slowly check every step. 是这个答案不是那个问题。Probably check that. I mean, it should be quick. But we can, if you are correct, you worry. Just I just listen to me. I'll forward it to you.
这些对我讲的有，我这个状态怎么回事？
Right. So two things. First, homework grading. If you have any doubt, question regarding the grading, please send an email to me, and I will ask RTA to double check. Right. So some mistakes are not are inevitable because within such a short amount of time, right? We need to grade over 100 homeworks. That's tremendous work. But if you have any question regarding your grading, send me an email, and I'll check to check. And if we find out you are correct, you're right, we'll give you the score, basically. Okay. And secondly, regarding the SFQ, I just checked only 2 students finished. You know SFQ, right? So please do that. ESFQ, right? ESFQ. We still have some time, I believe. Complete the survey, provide your feedback on how we can improve this subject. That's very important to us. All right. Right. So there's the next step is methanogenesis. That is to generate methane, right? Methanogens are the microorganisms. Methanogens, they are archaea Asian bacteria. So they are very old, right? Archaea bacteria that are distinguished from the true bacteria by a number of characteristics, including the position of membrane lipids, absence of the basic cellular characteristics, and distinctive rRNA. Right? So a unique type of bacteria. They are obligate anaerobies. What does obligate mean? No oxygen, right? No oxygen. So they cannot utilize oxygen. A rate-limiting species in anaerobic treatment, the last step is a rate-limiting step. Coexist or compete with sulfide-reducing bacteria for the substrate fed with sulfate-laden wastewater. Okay. Both are reduction reactions. Compete for the electrons. 2 classes of methanogens that metabolize acetate to methane are first type, methanosida. It's rod shape, low Ks, and higher affinity. Second type, methanosacina, right? Spherical shape, high Ks, and low affinity. Some picture of anaerobic microorganisms. This is fed with food processing wastewater. This is fed with chemical wastewater. They have different morphologies. Right. Methane production. Okay. So a simple process to calculate how much methane can be produced. How we approach this problem? Actually, first look at oxidation of methane. Right, you have 1 mole methane, it consumes 64 grams of oxygen. You can CO2 and water. And understand the condition, the volume of 1 mole of methane is 22.4 liter. The volume. And therefore, what is oxygen? What is oxygen? Oxygen, COD, right? COD. So we get 0.35 liter of methane per gram of COD. 22.4 divided by 64. Okay, that's how we get 0.35 number. 22.4 divided by 64. I hope everyone understands how we get 0.35. 1 gram of volatile solids is about 1.6 grams COD. 1.6 gram. Let me ask you this. You have calculated this. What is the COD of cells? Theoretical COD of cells. Introduction to wastewater treatment. What's the theoretical COD of cells? How we write cell? C5H7O2, right? What is the number? 1.42, right? 1.42 gram oxygen per gram cell. That's a theoretical value, right? You have calculated, and you have used in some of the calculations. And here we say that volatile suspended solids could be approximately taken as cells, right? So the real number is like 1.6. Okay, real number is like 1.6. 1.6. Therefore, the methane production from 1 gram of volatile solids, 0.56. 0.56. So why we do this? Anaerobic digestion of sludge, right? Of sludge. So we get sludge. Do you still remember the waste part? The waste part, QW times XW or XR. Active sludge process. The waste part. How much sludge we waste? Right? QW times XW. So what do we do with sludge? Anaerobic digestion. Okay, anaerobic digestion, we could produce some methane. In 1 gram of volatile suspended solids, you get 0.56 liter of methane. But of course, this is theoretical value, 0.56 liter. Right? If methane is only 65% of the gas composition, there could be some other gases. Right? The total gas production will be like this. But here you have different units to be feet and pound. Someone asked me during the break whether there will be converging of units during the exam. The answer is no. Okay, you will not be asked to convert between international units and American units. That only appears in the classroom practice problems and perhaps some of your homework, but not exam. Okay, not exam. Okay, this is how much we get the gas. All right, some pictures regarding anaerobic digester. Right, so they are huge. They are huge. These are the anaerobic digesters of municipal sludges. So the waste part, QW times XW. Also in Sha-Tian sewage treatment works. Okay, if you look at the aerial photo of the treatment plant, you will see big tanks. And if you have a chance to visit Sha-Tian sewage treatment works during their open day, they have open day, you will see all these large tanks as well. So there's methane produced, and sludge is treated. Okay, it's treated or stabilized. So we have some colleagues working on co-digestion of sludge and food waste. Okay, so food waste, organics, right? Organics. So we can mix municipal sludge with food waste and for the digestion. Right? We have some research going on campus, and I believe in Xiaohou 1, there's I believe O Park, the training facility O Park, right? So they are doing co-digestion of sludge and food waste as well. So by degrading the organics in sludge and food waste, we produce some energy. Okay, cattle feedlot. Right. So you can see here, anaerobic treatment is used in different scenarios compared to aerobic treatment, right? What is the feature of the sludge? What is XW? What's the typical range? Concentration over 10,000, right, milligram per liter. So it's very high concentration, And here, so we are talking about some agricultural wastewater, some industrial wastewater, high organic concentration, right? High organic concentration. So here the concentration in COD could be thousands or even more than 10,000. Municipal wastewater 500, right? So it's different scale. Anaerobic treatment is used in different scenario. Here is type of agricultural wastewater. Another example, right? Produce pipeline quality gas from agricultural biosolids, agricultural waste. You get some methane, of course, right? Cold down treatment in India as well as in mainland, old days, right? Right? 沼气, right? So it's the same technology. From landfill, okay? Landfill production of gas. Of course, sometimes you need to purify. As we said, it's not only methane, right? The gas contains other species. So here is a purification facility. And what we can use methane for? Electricity, we burn it, right? We get electricity and we get heat as well. So it's a process called CHP. So typically it's called CHP. What is this? Combined heat. I think combined heat and electricity production, or combined heat and power generation. Right? Combined heat and power. So it produces heat as well as electricity. And electricity can be used, for example, driving our aeration system, right? Bubbling, pump, etc. And it also can be connected into electricity grid. So that is a renewable kind of energy production. Methane from separated refuse in the US. And this is to some extent dangerous. I believe there was a news in Mainland a few years ago. There was explosion from the tank, right? So because it's huge and a lot of flammable gas. Right? Of course, we have some design for the anaerobic digester. Okay, you have to prevent oxygen, right? Prevent oxygen. This is an interesting design. It combines clarifier and digester, so it's called clarigester. It's clarifier and digester, right? This is the clarifier portion. This is the digester portion. The bottom, right, is anaerobic. So here, clarification. The anaerobic, typically we see upflow from the bottom to the top, like this. Okay. Anaerobic activated starch, sugar beet treatment, Sweden. You see this is a closed reactor. This is clarifier. Okay. Industrial wastewater treatment. And also we could make it like a filter, right? Trickling filter. I hope you still remember trickling filter. You have the media, right? You have the media for the microorganism to grow. But trickling filter, that is aerobic treatment, right? It requires oxygen. But here it's anaerobic, so it's closed. But within the tank, we have some media for the anaerobic microorganism to grow. Okay? Make sense? Does it make sense? Wheat, starch, waste, and run waste. Right? So one production, the waste. And it saves money. Okay, it saves money. If you can utilize the generated methane, electricity, heat, and so on, right? So that's why nowadays we're talking about carbon neutral or carbon negative wastewater treatment. Okay, wastewater treatment. So now wastewater treatment is consuming energy, right? But now many people are working on to make wastewater as a source of energy. It could be easy if the organic strength is high, like industrial wastewater, like the sludge, you can produce a lot of energy from that type of wastewater. But for municipal wastewater, organic strength is low, COD a few hundred, right? So energy density could be low. So that is a challenge. But it's a frontier topic, right? Some pilot study are going on at Stanford University, and also one of our colleagues did this before he left us to join Imperial College. So we have some pilot study in Stonecutter, still train works. We build some tank, try to harvest energy from our wastewater in Hong Kong. Okay, so some research is going on to make the energy production, positive energy production from wastewater, municipal wastewater, possible. Okay, so that's the frontier. The granules, anaerobic microorganisms. Okay, that's a picture of the granules. Okay, UASB. This is a very famous reactor type for anaerobic treatment. It's called upflow anaerobic / blanket reactor. In short, UASB. Okay, UASB reactor. What does the reactor look like? The influence comes from the bottom of the tank, right? It's still upflow. On the top, it's a gas outlet. We have methane produced and other gas produced, and they come out from the top, right? And effluent comes from somewhere here. Right? It's upflow, anaerobic, sludge, and blanket. Blanket, what does blanket mean? Think about different types of settling, right? Different types of settling. What is a blanket? What is blanket? Which type? Yeah, that's a blanket. Which type of settling? Right. So check it out. Okay, so this is used for the treatment paper processing wastewater in the Netherlands. This is actually used quite widely in industrial wastewater treatment. Okay, industrial wastewater treatment. Of course, this guy Latinga invented this reactor. Okay, and let's talk about the process. What's the time? Okay, let's talk about the process. First type is standard rate digester. Okay, standard rate, semi-continuous feed and withdraw. Now mixed closed tank. Say let's say 30 days. Is it long or short? Long or short? 30 days. Long or short? Long compared to 2 to 5 days of what? Theta of. So what's the theta say in aerobic treatment? Like active sludge. Active sludge. A few days. Right? A few days. You don't remember? 3.5. 3. So there is a page in the slide which compares all the data of different variations of the treatment process. Okay, but typically it's few days. So this is around 30 days. Solid retention time. Much of tank volume is not used for digestion. Okay, so active digestion zone volume selected, so that solid stay in the tank for a period of 30 days. Mixing in this zone is often accomplished by internal gas production. Right, you have gas produced, that creates turbulence. Right, so that makes mixing. The lower part of the tank is digested to hold, thicken, and digest the sludge a little more. Storage time for this part of the tank is about 90 days. Right? Digested sludge is more dense than fresh sludge, and therefore settles to the lower part of the tank. Right, let's look at the schematic. Right, this is inlet, this is outlet. We have different rooms within the tank. Active layer, right? Digestion happens. Supernatant, right? This is stabilized to concentrated or thickened solids, and we remove some solids from here, and gas comes out from the top. Right? It's conventional. Of course, you can have mixing. You can promote mixing within the tank. This one, you have gas. circulation. Right, gas circulation. How about, so earlier the previous one was standard rate. So how about high rate? High rate digester is two stage. We have a continuous phase stirred tank here, this stirred, followed by a stratified tank. That's a standard, right? Standard. Usually both tanks are identical so that one can serve as a backup. Mixing in the first tank is by gas recirculation, liquid recirculation, okay, through an external heat exchanger or by mechanical agitation. You have different ways to mix the liquid here. Usually the first stage, only first stage is heated. Different configurations, CSTR, right, contact process, upflow packed bed, downflow packed bed, fluidized bed, expanded bed, USB incorporating separate settler here, a baffle director, so we have baffles, which creates mixing, right, turbulence flow, perhaps, and two-stage leaching bed, and then membrane, solid separation. So here we have a membrane, so you can retain solids, it gives water, and anaerobic contact, okay, many configurations. And we will not go into the details regarding the application of each type of reactor. Right? Questions so far? Yes.
Have we memorized all the figures?
Nope. For this figure, it will not be tested basically. That's just for your knowledge. Okay. We focus more on these fundamentals. What is, for example, what is anaerobic treatment? What is anaerobic fermentation? What is anaerobic respiration? Right? How the microorganisms work together, right? And then so later, what is essential conditions? Right? How environmental factors affect anaerobic treatment? And then what's the difference between aerobic and anaerobic treatments? That's also important. Right? You should know that the application of anaerobic treatment is different from aerobic treatment, right? Because of different features. That's a part you need to understand, manage, and apply, but not this type of figure, because we do not talk about design, okay, or the process modeling, etc. So we'll not emphasize these reactors in this class or in this topic. Okay? But for aerobic, there we have done some process modeling, so you should be able to know different configurations of the aerobic treatment process, right? And that has been tested in previous exam papers. If you go to look at some of the papers, you'll see I ask them, as students, to draw some of this aerobic process. Okay. Okay. Any more questions? All right. No. All right. Essential conditions of anaerobic treatment: no oxygen, right? So the first condition, and no toxic inhibitory compounds. That's also understandable. Okay, that applies to aerobic treatment as well. No inhibition. Okay, pH. pH is important, which we will discuss. Almost neutral, right? Almost neutral. So why this pH range? It's a narrow pH range. Sulfation alkalinity. Okay, good. What is alkalinity? What is alkalinity? What is alkalinity? If you cannot answer this question, you should work out. Okay, alkalinity. Low volatile fatty acids and temperature range. Of course, nutrients and trace metals, right? Nutrients, metals, iron, cobalt, nickel, etc. And some time, operation time, SRT, HRT. So let's talk about environmental factors. The first one is temperature. So all biological processes depend on temperature. Okay, depend on temperature. Anaerobic system, 3 optimal temperature ranges, as we discussed this concepts: cyclophilic, methylphilic, and thermophilic. Right? Look at this. This is growth rate of methanogen. We see that methanogenesis is a rate limiting step. Right? So methanogen's growth rate is important. It is a function of temperature. Higher temperature, higher growth rate. So typically, rate of reaction doubles for every 10 degree rise in temperature, up to optimal temperature. But generally, rate doubles every 10 degree rise. pH, as we said, it's a narrow range. So how we get the pH? There exist 2 groups of bacteria in terms of pH optimal, namely acinogens and methanogens. The best pH range for acinogens is 5.5 to 6.5. For methanogens, 7.6, and 8. Therefore, the optimal pH is in between these two, right? Almost neutral, right? So you have to accommodate the 2 groups of bacteria. Okay, 2 groups of bacteria. Low pH reduces activity of methanogens, causing accumulation of volatile fatty acids and hydrogen. Right? At a higher partial pressure of hydrogen, propionic acid degraded material will be severely inhibited, therefore causing excessive accumulation of higher molecular weight fatty acids, such as propionic acid and butyric acid, and the pH drops further. That condition is known as sour or stuck. Right? You have a lot of acids. And what do we do if the pH is very low? What do we do? Increase the pH. How? How can you increase the pH? Add what? Add all this, right? This is bicarbonate, sodium hydroxide, sodium carbonate, right? Calcium oxide, and lime, calcium hydroxide, and ammonia. And then let me ask you, what is alkalinity? What is alkalinity? You failed the exam. What is alkalinity? The buffer, the capacity to buffer pH change, right? So more specifically pH drop. So that is sodium bicarbonate and sodium carbonate, right? Therefore, alkalinity is important because it's a buffer, right? So it could prevent the pH drop. Okay, it could prevent pH drop in your system, right? And therefore, okay, that's optimum, almost neutral. Right? You accommodate two groups of bacteria. Okay, alkalinity is important because in case you have a pH drop, alkalinity can work, right? Can work. Buffering capacity. Degradation protein produces ammonia, which reacts with CO2, forming ammonia bicarbonate as alkalinity. The degradation of salt of fatty acids may produce some alkalinity as well, the bicarbonate. Sulfate and sulfide reduction also generate some alkalinity. The capacity to buffer pH drop. Nutrients, right? Nutrients. Nitrogen and phosphorus, important. Okay, nitrogen and phosphorus. And some trace metals, nickel, cobalt, iron, molybdenum. This is selenium, right? This one.
Is that selenium?
Nutrients and trace metals required for the anaerobic process are much lower. Ratio COD to nitrogen to phosphorus. And toxicity. Okay, toxicity. Some toxic chemicals will be prevented. Heavy metals, right? Halogenated compounds, etc. It could inhibit the growth of the microorganisms. What is the time? How many pages we have? So we should finish. No, I cut many of the slides. You have only 40 something, right? Yeah. So let's continue and finish early. Okay. I want to reduce the burden, so I cut many slides. Sulfate. Okay. Earlier I mentioned the case of Hong Kong, right? So I have very high concentration of sulfate in our wastewater, and sulfate competed for electrons, and sulfate get reduced, and have hydrogen sulfide produced. Right. Part of COD is diverted to sulfide reduction, and therefore total COD available for methane production will be reduced greatly. So methane will be reduced, other gases will be produced. Right. Sulfide plus COD, sulfide reducing bacteria, hydrogen sulfide. Okay, H2S, hydrogen sulfide, which is smelly and toxic. H2S. Okay, hydrogen sulfide. Rotten egg smell, right? Sulfide will also impose toxicity to methanogens at a concentration of 50 to 250 milligram per liter as free sulfide. Sulfide. Okay. So we used to have a calculation here. So I cut that part. So if we have some sulfide in the wastewater, how much methane you get? Right? We have certain concentration of sulfide and how much methane you get, and we change the condition a little bit and what you get, etc. But I just skipped that part. Okay. So finally, let's compare anaerobic and aerobic. Okay, anaerobic and aerobic. First one, wastewater type. Wastewater type. What does loading rate mean? What is loading rate? Loading rate. Anaerobic. Compare this value. Anaerobic 10 to 40 kilograms COD per cubic meter per day. Aerobic 0.5 to 1.5 kilograms COD per cubic meter per day. The wastewater for anaerobic treatment has much higher COD. Right? Is it? We compare the number. 10 to 40 compared to 0.5 to 1.5. Okay? So what are these wastewater? High organic strength. Industrial wastewater. Sludge. Right? It's not a municipal wastewater. At least for now, for current technology. Aerobic municipal wastewater. Comparatively speaking, low organic strength. Biomass yield. Active sludge. So the yield. Typical number 0.4, 0.6, right? I hope you still remember the yield. The high biomass yield 0.35 to 0.45 kilogram VSS per kilogram COD. And biomass yield is fairly constant in respective types of substrate metabolized. For anaerobic treatment, the biomass yield is low. It's about 0.1 to 0.15 kilogram VSS per kilogram COD. Biomass yield is not constant, but depends on types of substrate metabolized. So here, anaerobic treatment, the growth rate of microorganisms is low compared to that in aerobic. Right. Specific substrate utilization rate, anaerobic treatment is high, 0.75 to 1.5 kilogram COD per gram VS per day. Aerobic 0.15 to 0.75. Okay. So this one is a few times higher substrate utilization rate. Startup time, anaerobic takes much longer, 1 to 2 months. For metaphilic, for thermophilic, 2 to 3 months. Right, 2 to 3 months. So it takes much longer time for you to run an anaerobic reactor. right, to grow, because the microorganism grows slowly there, so you need much time. For aerobic, pretty quick, 1 to 2 weeks. You could have an operating tank. SRT, what's the standard rate? Standard rate digester theta C. What's the number? In the earlier slides. 30 days, right? It's about 30 days. Aerobic, we said it's few days, 4 to 10 days. Much longer for anaerobic treatment. Microbiology, multiple groups of organisms in anaerobic treatment. Okay? Anaerobic treatment. And they degrade organic matters in sequential order, step by step, and they work together. Right? The later step will affect the earlier step. Aerobic meaning a one species phenomenon. Therefore, it's easier for you to control, relatively speaking, the aerobic process. Right? Anaerobic process because you have so many bacteria. Environmental factors, highly sustainable to changes in environmental conditions for anaerobic treatment. We talked about temperature, talked about pH, alkalinity, right? Nutrients, oxygen. All this affect anaerobic treatment. Aerobic, I mean, these factors affect aerobic treatment as well, but to a lesser degree. Okay, to a lesser degree. Less susceptible to changes in environmental conditions. All right, so final slide. We compare the aerobic process and anaerobic process in a material flow chart. This is anaerobic. If we start with 1 kilogram of biodegradable organics, we'll pretty much get, we have 50 around 50% for production of energy, right? Respiration, and 50% for biomass production, cell synthesis, right? This is a rough number, okay? It's a rough number. It's not necessarily 0.5. It could be 0.4, it could be 0.6. But for anaerobic process, biogas 0.9, biomass only 0.1. Okay, only 0.1. That is a yield. That is a yield. Also, in terms of electron donor and acceptor, waste is the electron donor. Oxygen is the electron acceptor in aerobic treatment. Anaerobic treatment, both electron donors and acceptors are wastes or organics, right? The original wastes and the intermediates. And you get methane. Okay, you get methane. I believe that's the last page. Ready to go? Right, any question? Any questions? No? So everyone is very happy. You can go early, but you paid the 3-hour tuition, right? All right, no? Okay. So I saved some slides because I think it's too much. It's already too much content. What we do in the final class, we will spend some time at the beginning to talk about water use, because we haven't talked about that, but we will not spend a lot of time. But still, we should talk about water by looking at the entire picture. Okay, entire picture. Then we'll go through homeworks. Okay, I'll go through the solutions of both homeworks, and I will not post the solutions in Blackboard. Okay, so you can come here, or you can watch the recordings if you miss next lecture. Okay, and then we'll briefly talk about exam composition, what kind of problems you are expecting, etc. Right, homework number 2 is due next Wednesday, right? Next Wednesday, so you should bring the hard copy to the classroom, and I will collect. But anyway, next class I will give you the solutions to homework number 2 as well, but not grading. It will take some time. Then I will send out an email when the homework number 2 is ready for pickup from my office. Basically, I will put all the homeworks in front of my office, and you can come whenever you are available to pick it up. Right, so that's the arrangement for the final lecture. Okay, SFQ. Remember to complete the survey, then start to prepare for the exam. Okay, prepare for the exam. You can find all the exam papers in the past years, and these are very helpful. Okay, these are very helpful. Okay, all right. So that's it. That's for today. See you next week.